Hello everyone. What we are going to do today is today we want to see what is principle of virtual forces and which will give us a method which is called unit load method. Okay. Now, if you remember, this was the this is the summary of the that we have discussed so far in last two lectures. We discussed the principle of virtual work for rigid bodies, and that essentially principle of virtual displacements. Then we also discussed we need to go beyond this principle to analyze the kind of structures the deformable body. And then we need to understand what is virtual force, and then what is external internal virtual work, and that is the thing that we are going to do today. Okay. Now, let us first understand what is virtual work, what is virtual force, and the associated virtual work. Okay. Now, suppose again consider the same object, then suppose this for some loading condition, for some load the object undergoes deformation like this, and this deformation is the actual deformation. If you remember, when we demonstrated the virtual work through virtual displacement, the displacement was virtual displacement, and the load acting on the structure was actual load. Now, suppose for some load the displacement of the structure of this object is this. Now, let us apply some virtual forces on this object, and these are some virtual forces. Now, remember one thing, again similar to the previous case where the actual force and the virtual displacement, they do not have any cause effect relationship. The virtual displacement were not due to the actual forces. Okay. Similarly, here these actual displacement and these virtual loads, they also do not have any cause effect relation. They have a similarity in a way, they have this same sense of direction, but the displacement, the actual displacement is not due to this virtual loads. Okay. Now, again consider d1, d2, d3 are the associated displacement at the point acting at the point of action of F1, F2, F3, the virtual loads, virtual forces. Then work done is equal to this will be d1. Okay, please correct it. This will be d1. This will be d1. This will be d2, and this will be d3. The work done will be F1, F2, F3. Again, this is F1, this is F2, and this is F3. Okay. Now, this is the work done. Now, then this work done is then virtual work here is the work done by the virtual forces. The forces are virtual, acting on a body which moving through actual displacement. Okay. It is just the opposite, just the difference between the virtual work due to the virtual displacement was the forces were actual, and the displacement the body undergoes that displacement was virtual, but here the forces are virtual, but the body undergoes, or the body is moving through the actual displacement. Okay. Now, this is virtual work due to the actual. So, now again in the previous case the forces were the displacement field was the conjugate to the force field, but in this case the force field which is conjugate to the displacement field. Okay. But again this displacement in the force field, they do not this displacement field is not the effect of this force, or this force field is not the cause of this displacement. They are totally independent. Okay. And the only thing is the force field should satisfy the static admissibility. Static admissibility means they should satisfy the satisfy the equilibrium condition. If you remember, we discussed what is static admissibility, and the displacement field, they should be compatible. They should satisfy the internal compatibility of the object. Okay. Now, then the principle of virtual work for deformable bodies, it says that external virtual work and the is equal to the internal virtual work. And what is external virtual work? Of course, the virtual work is due to the external forces, and the internal forces due to the external forces, internal forces developed in the structure in a deformable body, and associated virtual work is the internal virtual work. Okay. So, now work done by external forces and then work done by internal forces. Then whenever we say the work done, two important parameters, two important things are involved. One is the force and the displacement, and then the associated force field. In associated force field, it is called external force, and suppose this is the associated displacement field, which is d external and the force is F external. And similarly, the internal, this is the F internal force and this is the associated displacement. Now, we have not made any statement whether the forces are real and displacements are virtual, or the displacements are real or the forces are virtual. If you remember, we said that we want to derive a very general principle of virtual work and then see the principle of virtual displacement that we discussed in the last class. That is a special case of this general principle. Okay. So, in this case what is happening? The force could be real, and displacement is virtual, or the force could be virtual and the displacement could be real. Okay. Now, but only thing is, this displacement and this force field, they are conjugate to each other. So, they are conjugate to each other. Okay. Now, then what is safe before we actually go further in deriving the expression of the principle of virtual work, let us understand what do we mean by external. There are four parameters are involved here. Okay, external force, internal forces, and the external displacement and the internal displacement. Let us now understand, and these four ingredients, they constitute the principle of virtual work for deformable bodies. So, before we derive that, before we get that equation, let us understand what are these what are the internal and external forces and what are the external internal displacements. Now, let us consider a truss problem, and if you remember this truss, again we last week we solved this truss using equilibrium condition. We obtained the internal forces using equilibrium condition. Now, suppose these members are 1, 2, 3 are numbered like this. Now, if we draw the free body diagram of this object, then these are the reactions, and then we have force, external force at B. And then because of this external force, if we get the member force in each member force in all the members, then these are the member forces in different members. Okay. Now, this is how we, if you remember, this is how we are showing the member force. This means that if it is shown in the member, this means the member is in compression, and if it is shown in the member, this means the member is in compression. That is the sign convention we are following for member. Now, so force in these are the forces in different members. Now, this is the external force field and this is the internal force field, and this is F external and this is F internal. Okay. Now, and suppose this system we call system 1. So, system 1 is essentially a force field which has the external force and the internal force. Okay. Now, and these internal forces are due to these external forces. Okay. Now, let us, so this was the force field. Now, let us understand what is the displacement field. Now, again, this is the same truss. Suppose at point B we give some the point B undergoes some displacement in this direction. Okay. And this is dotted line shown here is the displacement in the truss. Okay. And how do we get the displacement? We apply some displacement at B, and the B goes to B dash, and this is this corresponding displacement is A. Okay. Now, what happens now, because point B goes to B dash, then the point C will go to C dash, and we assume that there is no change in length in member AB and BC. Therefore, the member AC, there will be a change in length in member AC will be in tension, and the elongation of this member, elongation of the members will be CC dash, and that is equal to 2 by root 3. Okay, and you can obtain this 2 by this value through some simple geometry. Okay. Now, this is called external displacement, because you are applying a displacement at joint B, okay, externally, and this is internal displacement. Internal displacement, it means that this CC dash, this displacement is due to the change in length in member AC. So, this displacement is due to the when we apply a load, every member has internal forces, and when the member has internal forces, if the member is deformable body, if the members are deformable, then the because of the internal forces, the member undergoes deformation, and that deformation is the internal displacement. In this case, the member AC will be in tension, and because of this tension, the length of member AC will increase, and the initial length of the member was AC, and after the elongation, the member becomes AC dash, and change in length is CC dash, and that is due to the internal forces developed in the member, and this displacement is called internal displacement. Okay. Now, then this is called system 2. So, system 1 is the force field, and the system 2 is the displacement field. And system 1 is, we have two forces in system 1, the external force and the internal force, and in system 2 you have two displacement, external and internal displacements. Okay. And how the external forces, internal forces are related? We apply a force on the object, we get the internal corresponding the forces in different members, and if we give some externally some displacement of the joints, and because of the displacements, the member within the member itself, there will be the member undergoes some deformation, and that deformation, that displacement is the internal displacement, and this displacement field is the say it is system 2. Okay. Now, then go back to our previous slide. So, this was the external virtual work, and the principle of virtual work says that external virtual work is equal to internal virtual work. And now, the work done by the external forces means this the forces is the external force into external displacement, and then force done by internal forces in the internal virtual work will be the internal forces into internal displacement. But please note here, this force system, okay, so they are equal. Okay. So, this is the principle of virtual work for deformable bodies. Okay. Now, this is, as I said, this is system 1 and this is system 2, but please note, system 1 and system 2, they are not related to each other. It is not, they do not have any cause effect relationship. It is not that because of system 1 we have system 2, or because of system 2 we have system 1. Okay. System 1 is independent to system 2. Okay. But only thing is, system 1 gives you the force field, which is the external force and corresponding internal forces, and the system 2 gives you the displacement at the joints and corresponding the internal displacement in different members. Okay. Now, so system 1, what constitutes system 1? The equilibrium constitutes system 1, because you see, when we apply some external force in a structure, some internal forces developed in different members, and the internal forces should be equal to the summation of internal forces should be equal to the summation of external force, right? And that is equilibrium condition. So, this system 1, the premise of system 1, what constitutes system 1 is the equilibrium, right? Now, similarly, what constitutes system 2? It is compatibility. Now, if we give some displacement at the at any joint, the member undergoes deformation, and when the member undergoes deformation, when the structure undergoes deformation, all the members undergoes deformation. But this deformation in the member should satisfy the internal compatibility. Okay. So this system 2, the compatibility, which is the basis of system 2. Okay. Now, this is called principle of virtual work. Okay, for a general principle of virtual work. Now, we have, as I said, we will see that principle of virtual displacement that we discussed in the last two classes is a special case of this generalized principle. Now, we have two situations. One is system 1 is real. If system 1 is real, meaning the force field is real, but system 2 is virtual, the displacement field is virtual, then we have principle of virtual displacement, which is exactly same we discussed in the previous classes. Now, if system 1 is virtual, means the force field is virtual and the displacement field is actual, then this is called principle of virtual force. Okay. Now, if you remember, now let us see how the principle of virtual force and principle from the applications point of view, how they are different. If you remember the last class, we said we demonstrated that principle of virtual displacement essentially the problems in statics are solved through geometry, and also we said that the principle of virtual forces, their problems in geometry are solved through statics. Let us demonstrate this quickly. Let us consider this example once again. Now, point B goes to B dash and this displacement is A, and this the point AC, the member AC undergoes deformation CC dash, and this deformation, recall, CC dash is equal to 2 root 3, and this can be obtained easily by geometry. So, it is essentially a problem in geometry, there is no statics required here. Okay. You apply a simple geometry, we get CC dash is equal to 2 root 3, but we will not apply geometry to find what is CC dash. What will apply? We will apply the concept of statics. Let us do that quickly. Okay. Now, this is the problem. And then we have a force like this. We have a force like this, which is F. And if you remember, then this is your AY, and then this is CY. Okay. And then this is the external force, right? This is FEXT, external. Okay. Now, let us draw the internal force system. If you remember, the forces in these members are, this is minus F by root 3, this is also minus F by root 3. You can just easily find out this is F by 2 root 3. This is the internal force in the member. Okay. This is because of this external force. So, this is F external and this is F internal. So, this is our system 1. This is system 1. Okay. Now, let us find the corresponding displacement, corresponding displacement field. So, this was the actual structure. Okay. And then displacement was this is the displacement. So, this distance is A. Okay. This is A, B, C. Now, this is the external displacement. This is going more to C dash. This is the external displacement applied. This is the displacement applied to joint B, and this is D external. D external, and then what is the corresponding internal? Internal will be, so this is A, B, C, and these go to C dash, and this distance is say delta, okay, and this is your d internal. Okay. This is d internal because this delta is due to the internal force developed in AC, but this A, to get this because of this A we have this internal force right here. So, this is system 2. System 2. Now, what principle of virtual work says? Principle of virtual work says that it says if summation of F external into D external is equal to summation of F internal into D internal. Okay. Now, what is F external? Now, F external, you see here, F external we have F external this into this. So, what we have this into this, that is the external virtual work, is equal to, should be equal to this into this. Now, this into this if we check, then these two forces will not contribute because in this direction there is no movement at point A and point C. The only force that will contribute is F. So, so this will be F multiplied by A, right. So, this becomes F into A. This is equal to, now let us find out, now what is, this is the internal forces in this member. Now, here it is given that member AB and member BC, they do not, there is no change in length in member AB and BC, only change in length takes place in member AC. So, it will be, so this will be, this is F internal. So, this is F internal AB into D internal AB plus F internal BC into D internal BC plus F internal AC into D internal AC, right. Now, F internal is minus F by root 3, but this D internal is 0 because there is no change in length AB. So, this is 0, plus this is again minus F by root 3 and this is 0 because again there is no change in member BC. Then plus this is plus F by 2 root 3, F by 2 root 3 into this distance is delta, this distance is delta. Okay. Now, if we have this, then what we have finally, F into A is equal to F by 2 root 3 into delta, and this gives us, now F gets cancelled, this gives us delta is equal to 2 root 3 A. So, delta is equal to, finally we have 2 root 3 A. Okay. Now, if we see the example, the problem, if we use the geometry, then you can get this value. So, essentially what we have done is, we have not solved, you see here, we have not solved any geometry problem. It is a purely static problem, but we actually solve the geometry problem. This we can simply obtain from geometry, but that problem is solved using statics. So, that is the difference between principle of virtual displacement, principle of virtual forces. Okay. There in principle of virtual displacement, we solve the problem of statics through geometry, and here we solve the problem of geometry through statics. Okay. Now, here you see the F gets cancelled, right. Here F gets cancelled. Since F gets cancelled, the any value of F if we give, then still we get, for any value of F we get delta is equal to root 3, delta is equal to this value. Okay. This now gives us a clue of developing a method. The method is, now since any value for any value of F, this is, we can obtain the same delta, give F is equal to 1. Okay. So, we apply F is equal to 1, get the external F external dx, F external F internal, and give then another system we have d external, d internal, which are conjugate to Fx conjugate to force field, and then apply the equilibrium, apply the principle of virtual work and get the corresponding displacement. Okay. Now, this unit, this we will see how to do this. This will this method is called unit load method. It is just we have obtained a clue from this example, but let us now understand what is unit load method. Okay. Now, what we will do is we will demonstrate unit load method through trusses today, and then solve some examples of trusses finding displacement through unit load method, and then after that we will see how this unit load method can be extended to can be used for beams and frames. Okay, plane beam plane frames. Okay. So, let us take a truss element, any truss element. Let us take a truss element. Okay. Now, we know that any truss elements, they are all a two force member. Now, suppose this truss element is it is identified as I. So, it is ith element, and the corresponding force in the ith element is Ni, that is denoted as Ni. Okay. Now, suppose length of this member is Li, area is Ai, and Young's modulus is Ei, and it satisfies linear elastic behavior. So, this is stress and strain, and corresponding the slope is the Young's modulus. Okay. Now, if the area of this member, if the area is A, then what is the stress developed in this? Stress developed sigma is equal to, that is Ni divided by Ai, that is the sigma. Okay. Now, if sigma is this, then what is how these stress and strain are related? We know that epsilon is equal to sigma divided by A divided by E, right. So, stress by Young's modulus gives us strain. Then if the stress is this, then what if the member is subjected to an axial load Ni, this could be compression, this could be tension, then what would be the strain epsilon I in this member? The strain epsilon I in this member will be, then if we substitute sigma here, then what we have is Ni by Ai Ei. If the strain in this member is Ni by this, then if the length of the member is Li, then elongation in this member, elongation in member E is equal to this strain multiplied by the length, and this becomes Ni Li divided by Ai Ei. Ni elongation is equal to this. Okay. And this is sometime written as so we have elongation is equal to Ni Li by Ai Ei. This is sometime written as Ei is equal to Fi into Ni, and where Fi is equal to Li by Ai Ei, which is called flexibility. We will discuss more on flexibility in subsequent weeks. Okay. But only thing that we need to remember from this is this expression. In a truss, if it is the axial force is Ni, and then Ai is called axial rigidity. Okay. Because you see, if Ai is more, then elongation is less, and so if Ai is more means more Ai means the member is axially rigid. So, axial deformation in the member will be less, that is why Ai is called axial rigidity. Okay. Now, great. So, what we need to now next what we do is suppose this is a truss. Okay. Now, these are the members 1, 2, 3, 4, 5. This is a statically determinate truss, and what we first construct is the force field. Okay. Now, suppose this is the reactions, and this is the these are the external forces. Okay. Now, because of these forces, suppose this member has internal forces like this. Okay. Suppose these internal forces are denoted as Ni. Okay. Now, this gives us the force field. Okay. So, this is external forces and the external forces and the internal forces. Okay. Now, suppose because the member undergoes a deformation like this. Okay. And the corresponding internal the length of the all this length of the members now become this. So, dl1 is the change in length in member 1, dl2 is the change in length member 2, and so on. Okay. And suppose and we have seen that change in length can be obtained, any jth member, the change in length can be obtained by this. Just now we have seen it. Okay. Now, consider a point K here, and this point K moves to K dash, and suppose this distance is dk, and suppose our problem is to find out this distance. We have already seen method of joints and method of sections to find out internal forces in truss, statically determinate trusses. Now, what we want to do is, now we want to do the deflection. We want to find out the deflection of any particular joints or different joints, and that we will be doing. We are trying to do through principle of virtual work. Suppose we want to find out what is the displacement of point K, of joint K. So, this is dk. We want the displacement in vertical direction, suppose. Okay. Now, so our problem is finding dk. Now, let us take the same truss and apply a virtual force in the direction at point K in the direction of dk. Okay. Now, because of this action of this force, virtual force, suppose these are the corresponding reactions. Suppose these are these are the internal forces in the member, and these internal forces are denoted as small n, and when small n is the internal forces in the member due to the virtual load. Okay, virtual load at K. So, N1K is the internal force in member 1 due to virtual load Fk, and similarly N2K is the internal force in member 2 due to virtual load Fk, and so on. Okay. Now, if we take this as system 1 and this as system 2. Okay. So, system 1 is what? System 1 has a virtual load, virtual force, external force, and corresponding internal forces. So, system 1 has system 1 is the force field. In this force field is virtual force field. Okay. The external force is virtual, and the corresponding internal forces we have, that is due to the virtual external force. So, this is external. This is system 1. And the system 2 is the real, system 2 is the displacement field, right. Now, displacement field is now real. So, this is essentially principle of virtual forces, where the force field is virtual and the displacement field is real. Displacement field is real and the force field is virtual. Now, if we apply the principle of virtual work between these two systems, considering these two systems, and then what it says, this is the virtual force field and this is the real displacement field. Okay. And this gives us, then apply the principle of virtual work, which says that summation of F external, the external virtual work is equal to internal virtual work. So, this is the external virtual work, internal virtual work. Okay. Now, what is the external load we have? External load we have in the system 1 is this, that is the external load. Okay. The points B and this is the point B will doesn't move. So, there is no work done by the reactions at point B. Now, reaction at point A is in horizontal direction, but this point does not move in horizontal direction. So, there is no contribution of A x. So, in external force field only force we have the F k, right, only force is F k. And then what are the internal force field? The internal force field is corresponding these internal forces. Okay. These internal forces, the internal force field. Now, this is the internal force field. Okay. Now, so this is the force in jth member due to force F k. Okay. So, now what is the external force? External force, you see, this is the external forces. This force is applied in the direction of dk. So, this is the external, this can be treated as external displacement, external d external, and corresponding delta L1, delta D2, delta 3. So, this can be viewed in this way. You apply so this is compatible displacement field. Okay. Now, if we apply a displacement dk here, then all the members will undergo deformation as delta L, and the member 1 will undergo deformation delta L1, delta 2, delta L2 for member 2, and so on, if we apply a displacement delta k in member k in vertical direction. Okay. So, external displacement will be this, and internal displacement will be delta N1, delta L2, and so on. So, in the external displacement is this, and internal displacement will be delta Lj, means it is the change in length in member j. Okay. Now, if this is so this becomes Fk into dk, and this becomes a summation of Njk into delta Lj. Now, we know that delta Lj is equal to this, just now we discussed. Substitute delta Lj in this equation, and then Fk is a virtual force, and this is true for any value of virtual force. Just give Fk is equal to 1. If you give Fk is equal to 1, and if you substitute this and this, substitute this and this both in this equation. Okay, both in this equation, then what we get is dk is equal to this. Okay. So, this is unit load method. Okay. Why it is unit load method? Because the virtual force that you are acting, this is unit. Okay. Now, what unit load method says is, just quickly let us see unit load method through now. If we want to find out, if suppose this is the structure and we want to find out what is the displacement in any particular direction, what we have to do is, we have to apply a virtual force of 1 unit load in the direction. Suppose this is the displacement we want in vertical direction, right. Therefore, the force needs to be applied in vertical direction. We apply a vertical force 1 unit load in the direction which we want to determine the displacement. Now, this force will this unit load, external unit load, the fictitious load or the virtual load, this will generate some internal forces. Okay. And then we also know the internal internal elongation of this member by this, and then apply take these as d external, d as f external, f internal, this is d external, and these are all d internal, substitute in this equation and get the final expression like this, and this is called unit load method. So, we have just introduced unit load method. Probably when you demonstrate unit load method through some examples, the concepts will be clear, and that we will be doing in the next class. So, next class what we do will determine the deflection of truss using unit load method. Okay. Then I stop here. See you in the next class. Thank you.